Thank you. Let's see, use the table feature of the graph calculator to determine that. Oh, okay, okay. So here's the neat thing. All right, let's do this on my digital calculator. The weird thing about determining if two parametric equations intersect is the fact that there's that third time dimension. You know, we very often consider it to be a time dimension, even though it might not be. Oh shit, that's the wrong thing, Jeff. Dadgummit. Let me open my calculator. There we go. So something you can do, let me show you what the table looks like in the graphing calculator for parametric equations. It's kind of nifty. So let me put this in there first, and then I'll share this. Let me get the right mode going. What do I have in here? Holy shit. All right, here we go. Oh, crap. Yeah. All right, there we go. Let's see, and then what else is it? T plus 3, T plus 3, and T plus 4. Let's see, 4T minus 4. Okay, so let me share this thing. Share. Bam. All right, so here I've got all my polar stuff in there. So for these to intersect, they have to actually, the curves have to meet at the right time. So look at how the table looks. Isn't this kind of cool? It's kind of cool. So let's see. So from this, did they give any? No, they didn't give any limits on this, did they? No. Okay, I like it. That's crazy. T plus 3 and 4T minus 4. Okay, looks good. Oh yeah, forget what works here. Okay, so you can kind of look backwards and see if anything looks like, see that's getting out of control here. It doesn't look like they actually go through the same spot, does it? No. I don't know if you got to this point. Were you able to make this table in your calculator?
You have to do it by 0.5 on T.
Ah, okay.
Yeah, I had to use the actual graph to figure that out, though.
Yeah, that's what I was doing. Like, I used the graph and I saw
Oops.
that it did intersect. But then I was just confused as how to get the T value, because what I did is I turned it into a rectangular form. And then I just put in those two.
Oh, all right, sure. So you can tell here, yeah, it looks like it meets at 4.5. That looks to be roughly 2, maybe.
But it
So
asks for the T value. So how do we find that?
All right, so watch. So like somebody said, you can see from the graph, it looks to be 4.5 comma, and it looks like it happens right in here. Do you see? I mean, because it looks like it met 4.5, right? Right in between these things. No? Yes? Maybe? All right, let me do this. Does that make any sense what he just said? So you can tell from here, it looks to meet about 4.5. Is that cool? For x equal 4.5, it looks like maybe y is 2. Are you with me out there?
Yes.
Okay, and then notice that that's pretty much right in between these two, right in between these two. So if you do change the window so that your step, let me see here. Oops, Jeff, not the window, the table. There we go. So table set right above window, right? Where's this table set? Then you can change this. This is how big of a step size your table does. And if you look at your table now, that's where they all meet, right there. Now here's the thing I was talking about. If they did go through the same point, but at different times. Now get this, you ready? that means they don't intersect. If I walk down the street and then 4 hours later, somebody else walks down that street, we never met, even though we physically were in the same place, right? Do you understand what I'm saying? So if the line of your rocket intersects the line that some other missile makes, but not at the right time, then I don't care that it intersected the line. It missed it. They didn't hit each other. I have no idea if what I'm saying makes any sense, but I agree. The idea of graphing it to get an idea of where it might intersect is smart. And then that gives you an idea of what to do with the table to make it more precise. But did you see that where it controlled the table? Second window, table set. So I can make the table start somewhere and I can make the table step by so much. Can you go over 54? Yes, I can do that next. Is that okay out there?
Yeah, that makes sense. Thank you.
Sure. All right. Somebody's asking about, let me see, what was that? Section 10.7, number 54. All right. I don't know what I'm sharing anymore. Let's try this again. Oh yeah, and this is asking you to figure out what this could possibly be, right? So there's a few different ways you could try to do this. But you notice a couple of things. What is the maximum Y and the minimum Y value, for example?
-5 and 5.
Yes, that seems to be on the Y-axis. It seems to be following a trig function where the amplitude is 5. What about on the X-axis?
-4 and 4.
Yeah. Now what you need to figure out. So that explains the A and the C. Now to figure out the B and the D, you have to figure out how many cycles fit on the X-axis, on the Y-axis, right? Or another way to do it, so that's the theoretical approach. The experimental approach is make B and D several things and start to see the pattern in what changing them does to the picture. Does that make sense?
I don't get what you mean by how many cycles it goes through. Can you?
Because what do the B and the D do with these functions? What does that control? The B right here, what does that control? Just look at the cosine function. Like A is the amplitude, what does B do? Does anyone remember? What does B do? What does B control or change? Does anyone remember? Am I frozen? All right. Here we go. Somebody's chatting at me. All right, so you guys are thinking too recently. I'm talking about way the shit back when we first graphed sine and cosine. So if I had something like this, sorry. Say again. Period. So the period of this would be 2 pi over 4, for example. All right, so let me clear this out. Clear. So it really represents, which one are you looking at? 54. All right. So what does it seem, for example, how many times does it meet, how do I say this? How many times does it attain its max and min in the X direction? So as it goes through its cycle, it attains it once, and then the minimum, and then the maximum, and then the minimum, and then the maximum, and then the minimum, and then it starts over, right? So you can see per cycle, how many times did it go through a complete, per time period, how many times did it go through a complete cycle? No, you don't like that? Let me see. Did they give a good, they probably didn't give a good example of this, did they? No, okay. No, okay. So if you look at, all right, somebody's asking me, is it 3? Is what 3? Are you talking about the number of cycles it goes through? So if I start here, yeah, okay. All right, so if I start here, let me see, okay. Oh, which one? Sorry, I keep going the wrong place. That's why it looked different. If I start here, it's at the max. So it's sort of like a normal cosine function, right? Starting at the max. And then it goes to its min, and then it goes back to its max. All right, so that's one complete cycle it's taken. That's one cycle. And then it goes to its min, to its max, to its min. That's another cycle. So it looks like, yeah. Right, so here's the max. So let me plot this out. Let me see. Oh, let's see, what do I want to say here? So it starts at 4, and then it goes down to -4 here. I'm sorry, where am I at? Yeah, right there. Starts at 4, it gets down to -4. And then a whole cycle would be once it gets back up to 4. That would be one whole cycle. So if it starts at 4, gets down to -4 there, and then it gets back to 4 here. So that's one whole cycle so far. And then it goes back to -4. So it's got to go down, up, down for it to get through another cycle. So down and up. All right. I don't know. Maybe I should label these. This is A. This is B. C. Right? D. And then E. Oops, let me put you up there. Too late. All right. And then it goes, whoops, where am I at? F. I'm going to run out of room. Oh, well. And then it goes back to A, right? So there's one cycle, 2 cycles, and a half, it looks like. Let me see. No, I got to go all the way out. Yeah, it looks like it's got 3 cycles. Yeah, so whoever said 3 is right. Looks like it's got 3 cycles. A to B to C, C to D to E, E to F to A. I love it. So it does have 3 cycles in there. Do you see how to break this sucker down? It's really weird because the X components by themselves are a function of cosine. So they are following in the X direction. It's just doing this, but purely in the X direction. The only reason I see it kind of splayed out is because at the same time, the Y is doing some stuff. So you can kind of merge the 2 approaches. You can get a guess from something like I'm doing right now, plug it in and see if it makes the same pattern. So you can kind of merge the 2 approaches. Does that help you start to tackle this? Oh, let me see. I got a yes. Okay. This one's definitely one of the harder questions because it's asking you to work with a graph that you're not used to at all. right? This is not a standard graph. This is not like the tall atomic symbol or something. I don't know what you would call this. No. I'm not going to put this kind of problem on the quiz, but you still got to do it for homework.
Can you go to problem 36 on this section, please?
Sure. Let me see. By the way, all right, well, let's talk about that in a minute. This guy?
Yes.
Okay. So they tell you what A and B are, and they ask you to graph it where t goes from negative pi to 0. Okay, so you can make a little table of values. This isn't a technology section, right? No. So they want you to do this by hand. So what's going on? What issue have you run into? So 36, this looks like 4 cosine of 7t, right? And this looks like, 4 cosine of t, right? Because it's a plus b, a minus b.
Yeah, and I made the chart, but I don't know. It keeps coming out weird. Like it doesn't look right. And I think it's because of the 7.
Yeah, the 7's going to be extraordinarily funky. You're going to have more in your table, because what would that 7 do? Your period becomes what? It goes through a whole cycle this quickly, right? Right. Is it yes? Yes.
So like what values would you choose to put into?
Yeah, so this is going to be a combination. This is a semi-silly problem, because 7, it just does not work well with any of our angles. I agree with that. So let me see. The crazy thing about this problem is you're going to have to use a calculator for quite a few of these, because you're going to have to use stuff like anything you normally would put in. Like you would normally start with pi over 6, right? Yes, or 0, but who cares about 0? You would normally start with pi over 6. You're now going to have to start with pi over 42. Do you see that? Do you see why? What's the first thing you do to inputs in this function? When you put a number in for
Divide
t.
them by 7.
Yes, so they can all be 1/7 as big as normal to have that same value come out.
But because of the domain.
Yeah, okay, so you're right. So it would be like negative pi over 6, but yeah, so negative pi over 42. So you could start with negative pi. That's obviously where you start with, because that's where everything starts. And that comes out nice. That comes out nice. Right? But if you want to get more usable stuff, your next input would be what? So if I start at negative pi, go to 0, it might actually be easier to go this way, to be honest, just to keep things straight in your head. So if you start at 0, then the next thing would normally be negative pi over 6, but you might want to use negative pi over 42. Or you might want to just focus on the fourths, right? You might just want to focus on the fourths, like negative pi over 4, which means you actually have to put in negative pi over 28, because everything is 1/7 for this guy. So this is just an idea of paying attention to what happens to your inputs. What happens to the numbers you put in? Because that's going to change, so if you put in numbers and the first thing that happens is they multiply by 7, that means that all your inputs can be 1/7 what they normally would be. No?
I don't know. I just don't like it. It's weird.
I know.
But I
I
get
know.
it.
It's weird. And there's not a damn thing wrong with, you know, if I wouldn't necessarily totally understand anybody who doesn't like get stuck and then just throws this in the calculator just to get a peek at what it looks like. Nothing really totally wrong with that, especially on a problem like this where the numbers are not really jiving with the stuff we kind of know. Do you see what I'm saying?
I had a question about like the arrows. Because for one of the problems, I like problem 9. On their answer key, they have the arrows pointing the other direction, but from my table, it seems like they'd be pointing a different direction. And so I was confused as to how don't you go from like -3 then to -2, the arrows pointing in that direction, right?
Yeah, so this is your first point, and then you draw your second point. When you connect them, the arrows point from this point to this point. Yes.
Yeah, that's what I did. And it like on their answer key, it was the other direction. And so that's what I was confused about.
And they definitely make some mistakes. So you go ahead and do the work, and when I take a look at it, I can see if they're right or if you're right. But I mean, I could take, let me see. I could take a look right now. Let me see. What is this? Send 7? Number 9? Yes. Okay. Let's see what these crazy people are doing. Good Lord. All right, here we go. Let's see. Yeah, they totally have it the wrong direction. That is kind of pathetic. Yeah, so you're right.
That made me mess up like all of the homework because I was confused. I thought I was doing the arrows wrong the whole time.
Let me see if they messed up anything else here. No, they got that one right. I don't know why they messed that one up. Yeah, I'm sorry. Yeah, you know, any solutions manual is going to have some typo somewhere. Oh shit! Now my whole screen is messing up. But yeah, you're right. That's their mistake for sure. All right, let me try to salvage my screen here. Hold on. All right, guys. Anything else? By the way, I don't think I've said this to everybody yet. Looking at, especially right now, getting questions from earlier in these chapters, we might as well just move the quiz to Monday. How's that sound, everybody? Is anybody upset about that possibility? Does anybody want to say anything to me? I'm not talking
You're my
to you,
favorite
Jeff.
professor right now.
No, stop it. Oh, no, I don't accept that. Okay. All right. Now, please, dear God, this next quiz is 10-4 through 10-8. We are already quite a ways through chapter 11. So my problem is, I don't know if you guys, I know a few of you guys have followed my advice. Some of you guys have turned in homework incomplete where you did every other problem. And I put at the top, finish this. And I told you, I'm going to do my job, but you do what makes sense to you. So I don't know if you guys are further along and just aren't turning it in because it's not finished, or if you really are, haven't done like a lot of sections out of chapter 10 yet. I don't know what the truth is. But I feel like it probably leans in the direction of several sections aren't looked at yet at all. So let's move it to Monday. I wanted to try to give you a stress-free Thanksgiving, but you know, now you got a quiz looming. It's just the way things work. I am also going to post next week or maybe before next week, a practice final. And I'll have a practice final solutions video. Finals coming. Anything else from homework, guys, or anything else in general?
I have a question from 10-5.
Sure.
Problem 42 and 45. They're kind of similar, but just like that little section.
Let's see, 42. screen is being freaky. There we go. 42. Yeah, I forgot to mention this weird little notation. Is everybody cool with what that notation means? Yes, we will get through. We might not do all of chapter 12, but we're going to do the important parts of chapter 12. Don't worry. This little cis thing, do you guys understand what that means? It's not like cis male or something, but it's, so let me see, 42. This actually means 6. I really, really dislike this. I normally enjoy things that make me write less, but I really don't like, I've never seen that before this book, to be completely honest. But what it means is this. So they're being all cute and saying CIS, shut up, whatever. Your book, you're free, so I'll let it slide. But I don't think that was the problem, right? So what is the problem here? Did we talk about that specifically? Let me see. We talked about adding and dividing. Did I skip talking about taking roots? Is that the problem?
Yeah, I don't remember like learning how to take the root of something.
So right here, you can see it's very similar. It's the same kind of idea as how we went from multiplying two things to multiplying n things.
Yeah,
So
and I used that also, but I don't know, it was just weird. My answers were coming out different, and so could you do a practice problem?
Yeah, let's do an example. Let's see. Let's do this example here. Let's see what happens. Is there anything weird about this problem, by the way? Let me see. It's got 100 degrees. That I don't think that comes out too weird at the end. Right? That was the one with 100 degrees. And they said take the, what would it say? Take the, where'd it go?
42.
Take the square root. Okay. Which you can see if you're taking 1 over n, so this would be 1/2, n would be 2. So you take the square root. So this would be theta over 2. So let's see, let's try this guy. So the cube root. Oh, that's true, Jeff. How did I, dadgummit. How did I skip this? This is the cool shit. All right. That's really silly, Jeff. Let me do something. Hold on. All right. I'm not going to make you memorize this, by the way, so don't freak out. So let's do this problem. I want to show you something. I'm a little upset at myself that I didn't do this. That's really bad. Z to the 1/3. So n is 3. Is that cool? So n is the whatever the root is that we're doing. So let's see. It's going to be 8 to the 1/3. And then it's cosine of 2 pi over 3 divided by 3. So it'll be cosine of 2 pi over 9 plus 2k pi, become a pi. Oh my gosh. Over 3 plus I sine, same thing. Pi, Jeff, what's the hell? Over 3, okay. Chabow! And they tell you that k is everywhere from 0 up to n minus 1. So in this case, k is going to go 0, 1, 2. So it kind of makes sense. There are 3 roots, right? This is completing. So sort of like this. Now watch this. Let me see. How do I say this? Well, okay, we'll do this a different way in a minute. Let's just finish this out. So this will be 8 to the 1/3 is 2. Is that cool? And so if k is 0, I get 2 cosine of 2 pi over 9 plus I sine of 2 pi over 9. So whatever the hell this stuff is at 2 pi over 9. Is this cool with everybody? You can just throw that in your old calculator. And then if k is 1, if I make k 1, I'll get 2 pi over 9 plus 2 pi over 3, which is, let me think, what am I doing? 6 pi over 9 and 2 pi over 9 is 8 pi over 9. And again, you can just throw that in the old calculator. And if k is 2, you know, I get 2 cosine, add another 6 pi over 9. Okay. All right. And just throw those in the old calculator and see what those, so you can throw this piece in the calculator and this piece in the calculator. So you can write that as some number plus some number I and so forth. Go ahead.
According to the answers, it didn't want us to do that. It wanted it to leave it as like
Oh,
two
okay.
Yeah.
That's an option too. If they want an exact answer, they should have said so. Let's see what this little thing does. Is it pretty cool so far? I mean, it's just really plugging stuff in. I'm not going to make you memorize this formula, but let me stop from. Is that all right?
Yeah, it was more like their answer key had something weird that threw me off, but I was doing it correctly.
All right. It could just, all right, let me see what they wrote here for the answers to this thing. This is curious. Yeah, okay. So they got the same thing. And they left it all like that. That's fine. It's kind of not satisfying. So, all right. And I don't know, it could be another typo in the answer key. So again, I'm not sure how to say this. Don't give the solution manual extra credence because they do have a couple of typos or something. I want you to realize this. Let me see. Where can I get some room for this? Let's do it right next to this formula so we're not all forgetting how to use this formula. Where'd you go, formula? Here we go. Okay. Watch this real quick. Let me see if I can do this real quick. If you're going to solve this equation, for example, don't we normally just get, if I just solve this directly, somebody could think that they got all the answers by doing this, right? But now we see there should be 3 answers to this. And of course, we know for 2 different reasons. X cubed equals 8 should have 3 answers because of the fundamental theorem of algebra. Whatever the highest degree is in an equation, that should have that many answers. Do you guys remember that, sort of? No, not at all. So if I say my complex number is 8, let me see if you guys can go with me on this journey. This is so cool. Stay with me now. How do I turn this into polar form? This is kind of a crazy question. So it's just 8 hanging out here. So what's the angle?
0.
0, kick ass. So to write this into the Z form, the polar form for complex numbers, R is 8 and the angle is 0. Become a cosine. And let's check this out. Sine is 0 is 0, so the complex part goes away. Cosine is 0 is 1 times 8 is 8. Yay! So that really seems like extraneous work. But now watch. So this is Z. So what's Z to the 1/3? It would be 8 to the 1/3 times cosine of 0 over 3, right? Just doing this. Plus 2k pi, become a pi. Why can't I do pi today? Over 3. Plus I sine of the same angle. 0 over 3 plus 2k pi over 3. Now stay with. So this would be 2 times. So if k is 0, this would be 2 times cosine 0 plus I sine 0. Isn't that, good Lord, Jeff, too many freaking parentheses. Isn't that just 2? Isn't that, of course, the answer we already knew? Now watch. Z to the 2, yeah, they're 2/3. Z to the 1/3 if k is 1 would be 2 cosine of 2 pi over 3 plus I sine of 2 pi over 3. And if k is 2, z to the 1/3 equals 2 cosine of 4 pi over 3 plus I sine of 4 pi over 3. Just following what these are telling me to do. Now look what that tells me. That tells me one answer is here, another answer is at 2 pi over 3, and the other answer is at 4 pi over 3. This is 2 pi over 3. This is 2 pi over 3, right? From 2 pi over 3 to 4 pi over 3 is 2 pi over 3. And this is 2 pi over 3. They are equidistant from each other. Every complex number, every number that I take a root of, all of the roots will be equidistant in terms of angles from each other. That is such a cool thing. And I'm almost certain nobody understands what I'm saying. Okay. Now, of course, how would I do this without using any of this? I would just subtract 8. So I'd factor this thing, right? It would be little dude, big dude. I could use quadratic formula, and that's how I'd get these. These are going to end up being complex answers here, right? That would be the answers I would get from the big dude from factoring this guy and using quadratic formula on it. So there's a whole other way to do that. And now I could do fifth roots. I can't do this. I can't do this shit with fifth roots, but I can do this shit with fifth roots. It's a very simple recipe to follow. It really, really is. If n is 5, I put a 5 there, and I put a 5 there, and I go up to 4. I mean, it's not a difficult process. It's a very different process than what we're used to. But visually, it's so satisfying to see these roots show up equidistant from each other. So, all right, maybe that's enough. I don't know if that helped at all. I don't know. But that might be another one. I have to look specifically at the answer key and see if they messed up. Okay. Anything else from homework, guys? So you still have parametric equations and their graphs, and then of course vectors.
I have one more question about parametric equations.
Yeah.
So if it's like, if the domain includes a point where it's undefined, like we say it's like divided by 0, would that kind of be like an asymptote where there would be nothing there? There'd be no point there.
Yeah,
like,
yeah.
There was like a problem, like 21 was similar to that. On 10.7.
Oh, I see. Yeah. So yeah, what value of t gives you trouble? Both of these.
Pi over 2.
Pi over 2, yeah. Because they both share the cosine on the bottom, right? So that, but the thing is, how do I say this? They both x and y go to infinity at pi over 2, right? Right? Did I freeze? No, okay. Is everybody with me? Both x and y here. Am I looking at, I'm looking at 21. Both x and y here go to infinity at t equal pi over 2. But we know that, let me think, how do I say this? Secant and tangent have a very common domain. So tangent, and it's tangent squared, which gets really kind of freaky. So remember, tangent normally looks like cubic, right? It looks like a cubic going through here. Now it's squared, so it's going to look like this. It's going to be really freaky. So tangent squared has a shape that looks more like secant does, because of course secant sits on top of cosine. So secant's going to look like this. Weehaw, weehaw. And they have the same problem areas, which is really interesting. So when you go to make a table of values, you're going to want to approach these, sort of like we've done with other problem areas. So how do I say this? Do you see how once you figure out what it looks like between negative pi over 2 and pi over 2, it's going to just repeat that? It's going to have the exact same value. So you really only have to worry about between negative pi over 2 and pi over 2. Does everybody see that? Well, let me be careful. The secant is going to be negative over here. So maybe you should do, let's see, right? Isn't secant going to be negative over here? Weehaw. So it is going to be a little bit different. And then tangent is going to do its thing again. So the x and the y values will sort of repeat. It's just that every other little area they live in, the x values would have the same values, just negative of what they were over here. Because x is going like secant. All right, I don't know what else to say. So this is going to come out to be really, really funkadelic for damn sure. I don't know if you try to plug this in the calculator.
No, we had to graph it by hand.
No. I mean, I really appreciate that. And you shouldn't try to plug it in the calculator too soon. You should try to do some of this. But if you get to a point where you're stuck, there really is nothing wrong with plugging in the calculator and looking at it to see what it's supposed to look like and getting some clues as to where you might be going wrong or why you might be fine. Do you see what I'm saying? There's nothing wrong with it. Just don't do it first. Try to do it by hand first. So what I'm saying is I would start with negative pi over 2, which you can't plug in there. That's undefined for both x and y, right? Right? And then you could try right next to negative pi over 2, you're starting to come back. So that'd be negative pi over 3, negative pi over 4, negative pi over 6, 0. Right? So that's what I would do here. And then once I get up to pi over 2, and again, I can't use pi over 2 because they would become undefined, both of them. Oh boy, my writing sucks so bad, but I think you get the idea. Then I have to invest. Then what I can do is when t becomes 3, get out of there, 3 pi. When I start over pi over 2 and keep going from there. So I start here, I start where I left off. Undefined, undefined. Stay with me now. Then what's right after pi over 2 is going to be what do you want to say, Jeff? Pi over 3 part. So it'll be 2 pi over 3, and then 3 pi over 4, and then 5 pi over 6, and then pi. And the nice thing about these is, the x values will have the same values. They'll just be the negatives of what they were. And the y values will be exactly the same values because now tangent just keeps repeating. In fact, that's what it would have done anyway. It's just now they're going to all be positive, except sometimes 0. I have no idea if that's helping anybody. The worse you are with your trig stuff, the harder this is going to be for damn sure. But it's not a bad idea when you have a more difficult parametric problem to just sketch out a graph of each of these by themselves. And I know I'm looking at the wrong problem right now, but just in general. That's exactly what I did here for myself. So that gave me an idea of what to do with the table of values in general. No, yes, maybe, no. You guys are like, why couldn't this have been a whole week off? What the shit? All right. I'm going to take that as an okay, Jeff. All right. Let's see. I don't think there's anything too freaky in 10.8, but you never know. I seem to be wrong about that sometimes. We need desperately to get back into, all right, so this is what sucks about all of this. You guys are back here. We have a quiz coming, so obviously this is going to be on your brains. But in the meantime, we've done a few of these, and you've forgotten partial fractions by now for sure, for example, right? Thankfully, I've posted the complete, everything that could happen to you for partial fractions. That handout is up on Canvas. So you can go back and take a look at that. We need to get back into matrices, but before I do, any other questions real quick? I'll take maybe one more question. And you guys remember that I have extra office hours on Tuesdays and normally on Thursdays, obviously not this Thursday, but right? You guys remember that? All right, so let's get back into matrices then. So let's just review the last thing we did, which was matrix multiplication. All right, hold on. You guys were here. So, do you guys remember how to do matrix multiplication? Let me see. Let's say this is 1, 2, -4, 5, 3, -1. Let's say B is, you could do it, Jeff. 2, -1, -3, 5, -4, 4. And I want to know what A times B is. Let me just write it like this. There, so it doesn't get too freaky. First off, can I do that? What do I check to see if I can do this multiplication? What's the dimensions of this guy?
3 by 2.
Yeah, so he's 3 by 2. What's the dimensions of this guy?
2 by 3.
2 by 3. So can I do A times B? 3 by 2, 2 by 3. Why can I do that? Why can I do this multiplication? Why will?
Multiplication.
Huh? Sorry?
Is it because it's multiplication and you do? Never mind.
So matrix multiplication will only work if the inner stuff matches. And I really want, I mean, just it's nothing to memorize. It's actually the only way I could multiply two matrices. Remember, I do one across and one down. Is if this is the same as this. There's 2 across. There's 2 down. That's why those have to match so that they each have somebody to go with. So the inner ones have to match, and the answer is going to be the dimensions of the outer stuff. So the answer is going to be 3 by 3. So let me write these next to each other. Let me see. So it's a little easier to keep our eyes on things. Jeff? remember, this whole thing is predicated on dot product kind of stuff. So these are collections of vectors. I can think of this as a vector and that is a vector and this is a vector and that is a vector, or these are vectors and these are vectors. It actually works either way, and it's dependent on the problem I'm doing. But all a matrix is it's another level above vectors. They're like, it's sort of like this. There's numbers and then there's points. And this has higher dimensionality than this does. But this is just a collection of two numbers, right? You guys kind of with me? Little point is a collection of two, and then I can go to 3D, and so it's still 3 points. So now vectors are these objects. Vectors are like numbers, not really, but they're these objects I could do shit with. And then matrices are collections of vectors, just like points are a collection of numbers. No idea if that's going anywhere. So how the shit, I know the answer. Knowing the answer's dimensions is useful. I know how big to make this damn thing. And let's see, why is it 3 by 3? Well, let's see. The way this works is I do the first row times the first column, and it's a dot product. So it'll be 1 times 2 is 2, plus 2 times 5 is 10. So I get 12. So the first row, first column is 12. Can somebody tell me what this is? What place is this? So that's the first row, first column. That is the, what place is that?
First row, second column.
So if I take the first row, second column, that's where that answer goes. First row, second column, -1 minus 8 is -9. So it's kind of nice. The thing you're working with from here and here tells you where it goes in the answer. So if I do 1, 2 times -3, 4, that's going to go at the end there. First row, third column. -3 plus 8 is 5. Become a 4. Okay. And then so forth. And then once you get this down, it's pretty simple. It's multiplication and addition. Two of the best things ever. Right? So you go -8 plus 25 is 17. 4 minus 20 is -16. Is everybody following? I always go across, down, across, down, across, down, right? So 12 plus 20, 32. Please tell me if you have no idea, if you don't see where something's coming from. Please. Please tell me.
I don't see it.
See what? Which part?
I'm
The
just
whole
trying
thing?
to, yeah,
All right.
just,
So let's
okay, one more time. How did you get, oh, I'm sorry. I didn't mean for you to.
That's all right. Sorry. Now watch. Take this vector and this vector, right? What's their dot product? It would be 1 times 2 plus 2 times 5.
Oh, okay.
All I'm doing. That's all I'm doing over and over and over till I go a little insane, and then I'm done. 1 times 2 plus 2 times 5 is 12. Now move over. Shabunk. So I was here, now I'm there. And I'm still here. 1 times -1 plus 2 times -4 is -1 minus 8 is -9. Now I move over. Shabunk. First row, third column. -3 plus 8, 5. All right, how's everybody doing? Please let this be nice. Compared to some of the stuff we're due, this is nice. And then we got, so just to continue real quick, 4 minus 20 is -16. Wait, Jeff. I think circling this threw me off. -8 plus 25 is 17. 4 minus 20 is -16. 12 plus 20 is 32. And then 6 and -5 is 1. -3 and 4 is 1. -9, and -4 is -13. I think that's right. All right. Once you see what you're doing, it might not make sense at the moment why we decided to do it this way, but it was obviously a choice we could make because it's a choice we did make. And there is a reason for this. The more you've ever used Excel, the more you understand matrices, because Excel uses matrix logic very often. Could I do B times A in this case? Would B times A work? So B is 2 by 3 and A is 3 by 2. Would that work?
Yes.
Totally. The insides match. How big will the answer be?
2 by 2.
2 by 2. So obviously it won't be the same as this dude. So that's another verification that commutativity does not hold for matrix multiplication. So do B times A real quick. You can see why mathematically it makes sense that the answer is more condensed, because now I'm doing a 3-component vector and a 3-component vector. I'm doing more calculations each instead of 2 by 2, and I get a whole bunch of those. I'm doing 3 and 3. There's not going to be as many of those. I don't know if that made sense. So we get 2 plus 4 is 6. Minus 9 is -3. That's what I get for that. And then 4 minus 5 is -1. Plus 3 is 2. And then 5 plus 16 is 21. Plus 12 is 33. And then 10 minus 20 is -10. Minus 4 is -14.
What grouping are you doing on that one?
I don't know. So you go across and you go down.
Oh.
So 2 plus 4 is 6. Minus 9 is -3.
Okay, got it.
Across, down, across. So that's why you could put a little arrow there and a little arrow there. And then you do it. And then you get done. And then you move the arrow over here. So you go there, there. Then you move this arrow down here. There, there. And then you move that over there. Yeah, yeah. Whatever you got to do visually, keep your eyes going the right way. I think I've been working with matrices so damn long, and you use them for so damn much. I don't know how you feel about them right now. You think they're just number shit inside of brackets that you make people do more shit with, Jeff. What the shit? But they are so unbelievably useful. Anybody at all interested in encryption? Do you know what encryption is? Yes. How about Photoshop kind of stuff? Like, I know there's better stuff than Photoshop. I'm not really big into manipulating images. But is anybody into that kind of stuff at all? Right. So matrices contain information about how to change something else. So this is so far ahead of us right now, but there's a lot more to matrices than this. But this is just the bare beginning. We got to start somewhere. Okay, what I want to do right now, before you get too far, is show you how to put matrices in your calculator. So you have a way to check your work as you go, so you don't go insane. I always try to keep all of us as sane as I can. I'm sort of a, what's the phrase? Lost cause. All right, let me see. So here, let me share this. So if you want to try this with me, you've got your TI calculator handy. I don't know if you've ever noticed the little matrix button right here. So if you hit second, X to the negative 1 to get to matrices. I want to go over to edit. So I can edit a matrix. So let's just pick matrix A. And let's make it A. Oh, I got to make it the right size. I went right past that. Dadgum you, Jeff. So what size is this? This is 3 by 2. So let's see, 3 by 2. Isn't that cool? Bam. So then you can put it in there. Let's see, 1. I don't think you guys need me to read this off to you. Cool. So matrix A is defined. So now let's hit the matrix button and go back to edit. Let's edit matrix B. Let's put matrix B in there, and it's 2 by 3. Where'd you go? Five negative 4, 4. Now, here's where the cool shit happens. Go back to matrix. Is everybody with me? You guys all right out there? Anybody else here? Me and Amber? Okay. Everybody else logged in and went to bed.
With you.
So, hey, sweet, thanks. So I got my top rows here. All right. So let's pick some matrices. So this is under names is how you pick them. Edit is how you build them or change them. So if I pick A, oh shit, am I still in? Oh yeah, that's the thing, Jeff. You should know better. Hit second quit. It's the same thing as your lists. I don't know if you guys have ever worked with the lists in here. There's a whole bunch of lists you can work with. You got to quit or else it thinks the next thing you're doing is going into the matrix. So you have to quit. Now let's go. And this really gets really repetitive. Go back into matrix, go to names. I can pick A times, go back into matrix, pick B. Let's see, is that the same thing I got? 12, negative 9, 5, 17, negative 16, 32, 1, 1, negative. Yay, Jeff. And then go into matrix, pick B, times, go into matrix, pick A. Jeff, matrix, get out of there. Dadgummit. Dadgummit. Jesus, Jeff. This is like watching Joe Biden try to conduct himself on Zoom. All right. Don't get me wrong. I love Joe Biden, but it's a shit show sometimes. All right. Times, get matrix. I swear to God. I swear to God. All right. All right. I love all of this. Times. There we go. Matrix A. All right. And then you get negative 3, 2, 33, negative 14. Yay. Okay. You with me? And if I try to do, of course, if I try to do B plus A, what should it tell me? Can I add matrix to B and A? Can I add them?
No.
No, they're not the same dimension. So let's see what it says. Oh, it says dimension mismatch. That makes so much freaking sense. Their dimensions don't match. You foolish human. Okay. So that's pretty cool. That's very useful. That is not the way to get answers. That's the way to check answers. All right. Now, let's do this. What time is it? We got no time. Fantastic. I'm going to plant a few seeds in your brains. That sounds borderline Geneva Convention problems or something. I don't know. So one thing that matrices can be used for is to model systems of equations. Let's see. Does it really have to work? Sure. Let's do this semi quickly. Is that really the same answer? Yes, Jeff. All right. All right. So let me show you. All right, I'm going to lay down some groundwork here. We'll get into it next time. I can rewrite this in matrix form. Do you guys remember synthetic division? Did we talk about synthetic? Of course we did. We talked a lot about synthetic. Remember what synthetic did? It took the variables out of the way and focused on the numbers, because those are what is important. So can somebody tell me what's the quickest way to kill a letter? This is that earlier section where we solved equations. Well, what's the quickest way? Equation 1, equation 2, equation 3.
Multiply. Nope.
Quickest way.
Add 1 and 2 together.
Add 1 and 2, I can kill an x, right?
Mhm.
And then I could kill x again between these two, maybe. Or you could have said add 2 and 3 to kill a y, right? And the z looks like z is a bad thing to try, right? It's not terrible, but it's not as good as these guys. So a matrix is like synthetic division in that it focuses our attention on the numbers, because the reason you guys knew that was the quickest way to do it, or even the person saying multiply this by 2 or whatever, you were looking at the numbers. So as long as the variables are in line, all that matters are the freaking coefficients. So why keep writing the stupid letters? Right? Why not just write and here I put a line here. I don't even know if the book does the same thing, to be honest. This line is like the equal sign. Is that right? No, Jeff. Can't see. There we go. Shoot it. Now, what good does this do anybody, Jeff? I don't. Oh, yeah, that's right. This is going to take getting used to. So you're not going to believe me when I say that this makes this much quicker. Can you imagine what if I gave us one more variable and one more equation? Can you imagine the work to do that by hand the way we did these before? Can you start to understand how disgusting that would be? If I add one more, if I add a W into each one of these, W, 2W minus 3W, and then add another frickin' equation, I'd have to kill one letter 3 times. And then amongst those, I have to kill one of those letters twice. And then, oh my God. If I figure a way out to use a matrix, if I added another row and another column, the work I'm doing would not grow that much. I can just attack it with the same process, with the same algorithm that we're going to build. It's immediately scalable. That's why this is so much better. So notice this. If I added row 1 to row 2, doesn't that kill that? So in a matrix, what is my goal? Find the key master. No, stop. In the matrix, what is my goal? What will tell me I'm done? Well, what will tell me I'm done here? When I know what x equals, when I know what y equals, and when I know what z equals, right? So that means that my goal in this matrix is to have x, no y's, no z's, number. No x, y, no z's, number. No x, no y, z, number. Wouldn't this mean x equals a number, y equals a number, z equals a number? That's my goal. My goal will always be these diagonal ones with everything else zeros around them. You guys understand? So what this makes this become, This was a chore. This is kind of more a number puzzle, but not even that. It's just kill. It's just, if I add row 1 to row 2, I'll only do one thing because we're basically out of time. So if I take row 1 plus row 2 and I put the answer in row 2, all right. Because what I want my matrix to do, I want it to have, at every step, I want it to have the best equations in it. And if I manage to kill a variable, isn't that a better equation? Because there's less unknowns. So if I add row 1 to row 2 and put the answer into row 2, I'm going to overwrite this stupid equation. Why? Because I want a 0 there in my goal, don't I? Do you start to understand the thought process is different? So 1 plus -1 is 0. 3 plus 1 is 4. -1 plus 3 is 2. 3 plus 3 is 6. And then the first row stays the same. And the last row stays the same. Can I make a 0 here? Isn't that something else I want? I mean, how would I make a 0 show up here? What would I have to do to make that happen? And also, for some reason, people start to believe they can multiply rows together. Could I multiply equation 1 to equation 2? I could. Do I want to? Wouldn't that have a shit ton of freaking foiling to do? Can you imagine that shit? So nothing you couldn't do here, nothing, whatever you would never do up here or you weren't allowed to, can you suddenly do here? This still represents these equations. So what can you do? I can multiply a row by something. I can add or subtract 2 rows together. I could divide a row by something because those are all things I could do with equations. So be really careful. Writing it like this doesn't mean I suddenly can do more. That's not at all what it is. This just focuses my attention. Go ahead.
For the goal, does it have to be in that order, or could the second one?
Not really. You're right. You're right. Technically, these could all show up in different orders, but that really is my goal. But it really doesn't matter where these ones are as long as you get 1 0 0 0 1 0 0 0 1 somewhere. Does that make sense?
Yeah, makes
The
sense.
reason,
Thank you.
especially when we're first learning this shit, I want you guys to keep with this. Just so you have a definitive goal to get to. But then the more comfortable you get, the more you can kind of realize the flexibility in this. Something else I highly recommend, in fact, it's a little more than a recommendation, is to finish a column out. What do I mean? Get 1 0 0 before you move somewhere else, because you'll start playing whack-a-mole. You'll make a 0 somewhere, and then you'll make a 0 somewhere else, but then you lost the 0 you just made, and then you go to do that, and then you lost another 0. You probably can't see how that could happen, but so if you go through them, do this, do this, do this, you're never gonna lose a 0 and drive yourself insane. So to kill this guy, I would multiply row 1 by what?
2.
-2.
Negative? Oh, I like the way you said -2. So if I took -2 row 1, add it to row 3, and put the answer in row 3. I don't want to put the answer here because I don't want to lose my beautiful 1 right there. Are you with me? I'm going to replace this dude.
Can you also multiply by 2 and then subtract row 1 by row 3?
Oh, sure. Of course.
Yeah, that's what I was trying to say.
No, you're fine. You're fine. I kind of like to keep it at the addition level so I don't make any negative mistakes in my head. Because I don't care how good at math you are, you're going to make negative mistakes in your head at some point. So I try not to have too much of that in my brain. Now watch this. This is the last thing I'll talk about because we're basically out of time. But to kind of cut back on the amount of writing I do. And again, you can write the whole matrix over and over if you want to, but watch what I do. I just put next to this what this would become if I did multiply it by -2. I'm not going to rewrite the whole damn matrix. So if I multiply each one of these by -2, I put next to it what it would be. Because do I want the first row to stay like this? Do I want the first row to be this forever? No, because I want a freaking 1 there. There's a 1 there. So I just want it to be this for the time it takes to add it to row 3. So let's see. This will be the last thing we do. First row is still 1, 3, negative 1, 3. Second row is still 0, 4, 2, 6. This row becomes 0, negative 7, 7, 0. That kicks ass. Become a 3. And then the next thing I would do is to divide this by 7. Do you see that? And then you get a beautiful negative 1 there that I can use to kill those. So you start to look for 1s so you can kill other things to make zeros around the 1. So the 1 is like a laser. It can kill whatever else you want it to. You can just crank it up by 3 or 7 or 2 and make it kill something else. Will you always be able to make 1s? No. We'll do some examples next time. What happens if I can't make a 1 somewhere? That's not that big of a deal. But does that make sense? You're trying to look for 1s so you can use the 1 to kill the other stuff around it like we did here. That's going to become negative 1. I can use it to kill these 2. By multiplying this by 4, I can adding it and so forth. Okay, I think that's enough. I did put up a handout up on Canvas related to this. This process is called Gaussian elimination. Does anyone know Gauss? Anybody ever heard of Gauss? Anybody ever work with magnetic fields or anything? Probably not. Okay. Anybody ever heard of a degausser? No? That's back in the day when we had, if you put a magnet next to your TV, it would get all freaky. And you have to degauss it. So Gauss actually had the units of magnetic field strength named after him. Gauss did way too much. Gauss is a dude, he's like, Gauss, what the shit? What? That's not fair, man. Leave some stuff for other people. Gauss is involved in almost every, holy shit. So this is named after him. This process is Gaussian elimination, which makes sense. We're eliminating, bam, making a 0. We're eliminating stuff. All right, that's enough. All right, let me know if you need to hang out. Otherwise, you are free to leave.
Thank you.
Anytime, guys.
Thank you.
One more day, we got big old break.